Good morning, students. Today we will be discussing about the principle of operation of the induction motor and slip. For the sake of simplicity, let us consider one conductor on the stationary rotor as shown in the figure A below. Okay, here you will see we have considered a cross-sectional view of the stator, some part of it, and the rotor. Okay, and one conductor is lying here. And further, we have discussed in the previous section that whenever three-phase supply is given to the induction motor, it produces a rotating magnetic field. And let us say this is the rotation of your magnetic field. It rotates in the clockwise direction. We have seen that. So let this conductor be subject to the rotating magnetic field produced when a three-phase supply is connected to the three-phase winding of the stator. Alright. Let the rotation of the magnetic field be clockwise. We have seen it in the previous lecture. A magnetic field moving in the clockwise direction has the same effect as a conductor moving in the anti-clockwise direction in a stationary field. Now since we have a clockwise direction, and this is your suppose conductor, so we can consider that if this is the direction of the magnetic field and this conductor is stationary, so we can assume that this conductor is acting in a direction opposite or anti-clockwise to the direction of this magnetic field, or we can say the motion of this conductor is in the anti-clockwise direction with respect to the stator magnetic field. Okay, this is as simple as that. If you are standing at a railway station, suppose, and the train is passing by you, then if the train is moving in this direction, okay, and you are stationary, then if I want to consider your motion with respect to this train, then I can say you are moving in the opposite direction because the train leaving you in this direction. Alright. Now by the Faraday's law of electromagnetic induction, a voltage will be induced in the conductor. Alright, because these are the magnetic lines of force which are from stator to the rotor in the air gap. Alright, so when magnetic field lines will be cut by this rotor conductor, and EMF will be induced in that conductor. We know that. Okay, so by the Faraday's law of electromagnetic induction, a voltage will be induced in the conductor. Okay, since the rotor circuit is complete, now we have seen the construction of the three-phase induction motor, whether it is your slip ring induction motor or it is your squirrel cage induction motor, the rotor circuit is complete. Okay, since the rotor circuit is complete and there is a, you can say, since the rotor circuit is complete and there is a voltage induced in the rotor conductors, then what will happen? There will be a current flow in the rotor conductors. A current will definitely flow in the rotor conductors. And since current is going to flow in the rotor conductors, and we are about to find out the direction of this current, induced current in the rotor conductor, which direction it will flow. So we can easily find out this by the Fleming's right hand rule, by applying the Fleming's right hand rule. As you can see here, this is the motion of the conductor relative to the field. We have discussed it yet right now, because the field is rotating in the clockwise direction. Okay, so the motion of the conductor with respect to this field will be opposite, exactly opposite to it. And this is, we know that the direction of the magnetic field is from stator to rotor in the downward direction. So now apply the right hand rule. Your motion of the conductor is acting in the anti-clockwise direction, and the direction of the magnetic field is downwards. So if we apply the Fleming's right hand rule, we will get that this conductor is now having a dot polarity, or the current is coming out from the conductor. Okay. Since the magnetic field is rotating in the clockwise direction, okay, we have discussed it here. This is the direction of your magnetic field, clockwise. The magnetic field is rotating in the clockwise direction, and the conductor is stationary. We can assume that the conductor is in motion with anti-clockwise direction with respect to the magnetic field. Alright. Then by the Fleming's right hand rule, the direction of the induced current is outwards, as shown in figure B. As shown in figure B here, outwards. Alright. Then the current in the rotor current, now we have understood and we have found out that the direction of current will be outwards. Now this current in the rotor conductor will produce its own magnetic field. Okay, and this is shown in figure C. This dot polarity, if we apply the right hand thumb rule or your corkscrew rule, you will find out that this conductor or this current will have its own magnetic field. Now again consider the first case, that we have a stator, we have a rotor, we have a conductor whose polarity we have found out that it's a dot polarity. Magnetic field is rotating in the clockwise direction. Now what will happen? Now we know that when a current carrying conductor is placed inside a magnetic field, what will happen? It will experience a force, and this force is produced on the rotor conductor. ओके जब भी मैग्नेटिक फील्ड में हम क्या करेंगे, किसी करंट कैरिंग कंडक्टर को प्लेस करेंगे तो इसके ऊपर एक फोर्स लगता है, ठीक है, एंड दिस फोर्स विल बी प्रोड्यूस्ड ऑन द रोटर कंडक्टर. And now the direction of this force, we are interested in finding out the direction of this force, that in which direction force will act on this conductor. Okay, can be found out by the applying Fleming's left hand rule as shown in figure D. Here we will apply the Fleming's left hand rule. So this is your we are interested to find out force. Okay, so we know the current, dot polarity, magnetic field we know. Apply the Fleming's left hand rule, you will find out the force on the conductor will be in the clockwise direction, or in the same direction as the direction of your rotating magnetic field. Okay, so it is seen that the force acting on the conductor is in the same direction as the direction of the rotating magnetic field. What this means? This means that if we apply three-phase supply to an induction motor, what will happen? Rotating magnetic field will be generated in the stator, which will rotate at the synchronous speed. Then the conductors, the rotor conductors, will induce a current due to this changing magnetic field, and due to this current a force will act on the conductors, which will try to move these conductors or rotor in the same direction as the direction of your stator magnetic field. Alright, now since the rotor conductor is in the slot on the circumference of the rotor, we have considered only one rotor conductor, and that too was on the rotor slot. Alright, so this force will act in a tangential direction. Obviously it will act in the tangential direction to the rotor and develop a torque. Similar torques are produced on all the rotor conductors. Since this was only one conductor, so all the rotor conductors will experience the same kind of torque. Since the rotor is free to rotate, so it will start rotating in the same direction as the rotating magnetic field. Alright, Therefore, we can say that the three-phase induction motor is what? Is self-starting. And now, since the operation of this motor depends upon the induced voltage in its rotor conductors, and hence it is called the induction motor, because its operation is mainly due to the induced voltage in the rotor conductors. That's why it is called the induction motor. Alright, so this was all about the principle of operation of the induction motor. Now we will discuss about the speed and the slip. Now, since the induction motor rotor, we're talking about the rotor, cannot run on the synchronous speed. Why it cannot run on the synchronous speed? Now consider for a moment that the rotor is running at a synchronous speed. So under what will happen under this condition? Under this condition, there would be no cutting of flux by the rotor conductors, because both the stator magnetic field and the rotor, if are moving at the same speed, there is no relative motion between the two, and there will be no flux cut by the conductors, and no EMF will be induced, hence no voltage will be generated, which will amount to no current, and hence no torque will produce, because the torque will only be produced if a current carrying conductor is placed inside a magnetic field. But since the two stator and rotor magnetic fields are running at the same speed, if they are running at the same synchronous speed, there will be no generated voltage, which will amount to no current, and further no torque, which eventually means that the rotor will not rotate. Hence, the rotor speed is therefore slightly less. This is also due to inertia. Alright, the inertia of rotor also tends to keep its speed low as compared to the stator synchronous speed. Alright, therefore the rotor speed will be slightly less than the synchronous speed, and therefore an induction motor may be called as the asynchronous motor, the motor which cannot run on the synchronous speed. Alright, now the difference between the synchronous speed and the actual rotor speed is termed as slip speed. Alright, so the slip speed expresses the speed of the rotor relative to the field. Alright, that how much speed it is in relation with the field. Okay, so ns, if ns is given by the synchronous speed in rpm, then nr is the actual rotor speed in rpm, then what will slip speed? Then what will be the slip speed? It will be equal to ns minus nr rpm. And also the percentage slip is given by, if we want to express this slip speed or slip in terms of percentage, it is always almost it is always mentioned in terms of the percentage. Then it is given by ns minus nr upon ns into 100. Alright, the slip at the full load varies for about 5% for the small motors and for about 2% for the large induction motors.